Chapter 12. Electromagnetic Induction. Exercises pages 286 to 287. Exercises Q1.1, page 286. Choose the correct option. A circular coil of 100 turns with a cross-sectional area of 1 square meter is kept with its plane perpendicular to the magnetic field of 1T. The magnetic flux linkage is 1 Wb2, 100 Wb3, 50 Wb4, 200 Webers. Solution: 100 Webers. Exercises Q1.2, page 286. Choose the correct option. A conductor rod of length L is moving with velocity v in a direction normal to a uniform magnetic field B. What will be the magnitude of induced EMF produced between the ends of the moving conductor? Solution: BLV. Exercises Q1.3, page 286. Choose the correct option. Two inductor coils with inductance 10 mH and 20 mH are connected in series. What is the resultant inductance of the combination of the two coils? Solution: 20 mH. Exercises Q1.4, page 286. Choose the correct option. A current through a coil of self-inductance 10 mH increases from 0 to 1A in 0.1 s. What is the induced EMF in the coil? 1. 0.1 V2. 1. V3. 10 V4. 0.01 volts. Solution: 0.1 volts. Exercises Q1.5, page 286. Choose the correct option. What is the energy required to build up current of 1A in an inductor of 20 mH? 1. 10 mJ2. 20 mJ3. 20 J4. 10 J. Solution: 10 millijoules. Exercises Q2.1, page 286. Answer in brief. What do you mean by electromagnetic induction? Solution: the phenomenon of production of EMF in a conductor or circuit by a changing magnetic flux through the circuit is called electromagnetic induction. Exercises Q2.2, page 286. Answer in brief. State and explain Lenz's law in light of the principle of conservation of energy. Solution: Lenz's law. The direction of the induced current is such as to oppose the change that produces it. The change that induces a current may be 1. The motion of a conductor in a magnetic field, or 2. The change of the magnetic flux through a stationary circuit. Explanation. Consider Faraday's magnet and coil experiment. If the bar magnet is moved towards the coil with its end pole facing the coil, as in the shown first figure, the number of magnetic lines of induction pointing to the left through the coil increases. The induced current in the coil sets up a magnetic field of its own pointing to the right, as given by Ampere's right-hand rule, to oppose the growing flux due to the magnet. Hence, to move the magnet towards the coil against this repulsive flux of the induced current, we must do work. The work done shows up as electric energy in the coil. When the magnet is withdrawn, with its end pole still facing the coil, the number of magnetic lines of induction pointing left through the coil decreases. The induced current reverses its direction to supplement the decreasing flux with its own, as shown in the second figure. Facing the coil along with the magnet, the induced current is in the clockwise sense. The electric energy in the coil comes from the work done to withdraw the magnet, now against an attractive force. Thus, we see that Lenz's law is a consequence of the law of conservation of energy. Exercises Q2.3, page 286. Answer in brief. What are eddy currents? State applications of eddy currents. Solution: whenever a conductor or a part of it is moved in a magnetic field, cutting, magnetic field lines, are placed in a changing magnetic field, the free electrons in the bulk of the metal start circulating in closed paths equivalent to current-carrying loops. These loop currents resemble eddies in a fluid stream and are hence called eddy or Foucault currents, after Jean-Bernard Léon Foucault, 1819–68, French physicist, who first detected them. Applications: 1. Deadbeat galvanometer. A pivoted moving coil galvanometer used for measuring current has the coil wound on a light aluminum frame. The rotation of the metal frame in the magnetic field produces eddy currents in the frame which opposes the rotation, and the coil is brought to rest quickly. This makes the galvanometer deadbeat. 2. Electric brakes. When a conducting plate is pushed into a magnetic field, or pulled out, very quickly, the interaction between the eddy currents in the moving conductor and the field retards the motion. This property of eddy currents is used as a method of braking in vehicles. Exercises Q2.4, page 286. Answer in brief. If a copper disc swings between the poles of a magnet, the pendulum comes to rest very quickly. Explain the reason. What happens to the mechanical energy of the pendulum? Solution. As the copper disc enters and leaves the magnetic field, the changing magnetic flux through it induces eddy current in the disc. In both cases, Fleming's right-hand rule shows that opposing magnetic force damps the motion. After a few swings, the mechanical energy becomes zero and the motion comes to a stop. Joule heating due to the eddy current warms up the disc. Thus, the mechanical energy of the pendulum is transformed into thermal energy. Exercises Q2.5, page 286. Answer in brief. Explain why the inductance of two coils connected in parallel is less than the inductance of either coil. Solution. Assuming that their mutual inductance can be ignored, the equivalent inductance of a parallel combination of two coils is given by Exercises Q3, page 286. In a Faraday disc dynamo, a metal disc of radius r rotates with an angular velocity omega about an axis perpendicular to the plane of the disc and passing through its center. The disc is placed in a magnetic field B acting perpendicular to the plane of the disc. Determine the induced EMF between the rim and the axis of the disc. Solution. Exercises Q4, page 286. A horizontal wire 20 meters long extending from east to west is falling with a velocity of 10 meters per second normal to the Earth's magnetic field of 0.5 times 10⁻⁴. What is the value of induced EMF in the wire? Solution. Data. L equals 20 meters, V equals 10 meters per second, V equals 0.5 times 10⁻⁴. The magnitude of the induced EMF. E equals BLV equals 5 times 10 to 5 20 10 equals 10 to 2 V equals 10 millivolts. Exercises Q5, page 286. A metal disc of radius 30 cm spins at 20 revolutions per second about its transverse symmetry axis in a uniform magnetic field of 0.20 T. The field is parallel to the axis of rotation. Calculate A. The area swept out per second by the radius of the disc B, the flux cut per second by a radius of the disc C, the induced EMF between the axle and rim of the disc. Solution. Data. R equals 0.3 meters, F equals 20 rps, V equals 0.2 T. A. The area swept out per unit time by a given radius equals the frequency of rotations x, the area swept out per rotation equals F pi r2. Equals 23.142 times 0.09 equals 5.656 m2. B. The time rate at which a given radius cuts magnetic flux. Exercises Q6, page 286. A pair of adjacent coils has a mutual inductance of 1.5 H. If the current in one coil changes from 0 to 10 A in 0.2 S, what is the change of flux linkage with the other coil? Solution. Data. M equals 1.5 H, I1I equals 0, IIF equals 10 A, delta T equals 0.2 S. The flux linked per unit turn with the second coil due to current I1 in the first coil is phi 21 equals MI1. Therefore, the change in the flux due to change in I1 is delta phi 21 equals M, delta I1 equals M, I1F, I1I equals 1.5, 10 to 0 equals 15 Webers. Exercises Q7, page 287. A long solenoid has turns per unit length 1.5 by 103 per meter and area of cross-section 25 square centimeters. A coil C of 150 turns is wound tightly around the center of the solenoid. For a current of 3A in the solenoid, calculate A. The magnetic flux density at the center of the solenoid. B. The flux linkage in the coil C. C. The average EMF induced in coil C if the current in the solenoid is reversed in the direction in a time of 0.5 s. Micro 0 equals 4 pi x 10 to 7 h per meter. Solution. Data. N equals 1.5 by 103 meters minus 1. A equals 25 x 10 to 4 m2. NC equals 150. I equals 3A. Delta T equals 0.5 s. Micro 0 equals 4 pi x 10 to 7 h per meter. 8. Magnetic flux density inside the solenoid equals 5.656 times 10 to 3 T equals 5.656 mt. B. Flux per unit turn through the coils of the solenoid, phi m equals Ba. Since the coil C is wound tightly over the solenoid, the flux linkage of C is NC phi m equals NCBA equals 150, 5.656 times 10 to 3 25 times 10 to 4. Equals 2.121 times 10 to 3 Wb equals 2.121 milliwebers. C. Initial flux through coil C. Phi A equals NC phi m equals 2.121 times 10 minus 3 webers. Reversing the current in the solenoid reverses the flux through coil C, the magnitude remaining the same. But since the flux enters through the other face of the coil, the final flux through C is phi A equals 2.121 times 10 minus 3 webers. Therefore, the average EMF induced in coil C. Exercises Q8 page 287. A search coil having 2000 turns with area 1.5 square centimeters is placed in a magnetic field of 0.60 T. The coil is moved rapidly out of the field in a time of 0.2 s. Calculate the induced EMF in the search coil. Solution. Exercises Q9 page 287. An aircraft of wingspan of 50 meters flies horizontally in the Earth's magnetic field of 6x 10 to 5 T at a speed of 400 meters per second. Calculate the EMF generated between the tips of the wings of the aircraft. Solution. Data. L equals 50 meters, B equals 6x 10 to 5 T, V equals 400 meters per second. The magnitude of the induced EMF. E equals BLV equals 6 times 10 to 5, 450 equals 1.2 volts. Exercises Q10 page 287. A stiff semicircular wire of radius r is rotated in a uniform magnetic field B about an axis passing through its ends. If the frequency of rotation of wire is f, calculate the amplitude of alternating EMF induced in the wire. Solution. In one rotation, the wire traces out a circle of radius r, i.e., an area A equals pi r2. Therefore, the rate at which the wire traces out the area is. Exercises Q11 page 287. Calculate the induced EMF between the ends of an axle of a railway carriage 1.75 meters long traveling on level ground with a uniform velocity of 50 km/h. The vertical component of Earth's magnetic field BV is 5 times 10 to 5 T. Solution. Exercises Q12 page 287. The mutual inductance of two coils is 10 millihenries. If the current in one of the coil changes from 5A to 1A in 0.2 s, calculate the EMF induced in the other coil. Also calculate the induced charge flowing through the coil if its resistance is 5 ohms. Solution. If delta Q2 is the charge that flows through coil 2 due to the changing current in coil 1, the induced current in coil 2 is. Exercises Q13 page 287. An EMF of 96.0 mV is induced in the windings of a coil when the current in a nearby coil is increasing at the rate of 1.20 a/s. What is the mutual inductance M of the two coils? Solution. Exercises Q14 page 287. A long solenoid of length L, cross-sectional area A and having N1 turns primary coil, has a small coil of N2 turns secondary coil wound about its center. Determine the mutual inductance M of the two coils. Solution. Exercises Q15, page 287. The primary and secondary coils of a transformer each have an inductance of 200 x 10 to 6H. The mutual inductance between the windings is 4 x 10 to 6H. What percentage of the flux from one coil reaches the other? Solution. Exercises Q16, page 287. A toroidal ring made from a bar, of length 1 meter and diameter 1 centimeter, bent into a circle. It is wound tightly with 100 turns per centimeter. If the permeability of the bar is equal to that of free space, calculate A. The magnetic field inside the bar when the current through the turns is 100 A. B. The self-inductance of the coil. Solution. Data. L equals 1 meter, D equals 1 centimeter, N equals 100 centimeters minus 1 equals 104 meters minus 1. I equals 100 A, mu 0 equals 4 pi times 10 to 7 H per meter. The radius of cross-section, R equals D, 2 equals 0.5 centimeters. Equals 5 times 10 minus 3 meters. A. Magnetic field inside the toroid. B equals mu 0 N equals 4 pi times 10 to 7, 104, 100. Equals 0.4 times 3.142 equals 1.257 T. B. Self-inductance of the toroid. Exercises Q17, page 287. A uniform magnetic field B, pointing upward, fills a circular region of radius S in a horizontal plane. If B changes with time, find the induced EMF. Solution. The area of the region, A equals pi S2, remains constant while B equals BT, as a function of time. Therefore, the induced EMF